Welcome back to Lecture 3. In this lecture, we are going to speak about some properties of the real numbers and solve a couple of examples based on these properties. Then we will talk about the supremum and infimum and what we mean by bounded set. We will concentrate only on real numbers, and we will not go beyond this into some other metric spaces. Based on my experience, if you understand the real number, then going into higher dimensions or into different metric spaces, it's going to be easy for you. Let's start from defining some type of number. So the first is natural numbers. So natural numbers are counting numbers. For example, 1, 2, 3, and etc. So we denote it by n, and if we say n belongs to n, it means n is a small n is a natural number. Since the natural number sometimes is limited, so we enlarge it by joining the negative integers and 0, and we call it integers. And denote by z. In some problems, we want to deal with the division. We denote the larger number systems by rational numbers and call it q. So the rational numbers are the numbers that can have the following form: m over n, where m is in z and n is in z. But not all numbers are rational. Not rational numbers called irrational. For example, square root 2, we prove that is a irrational number. So usually we often refer to the real number system as a real line, and we think about it as some geometrical object. The other thing you may notice, but we are not going to prove it, that the real number system is an order field. By order field, it means if we have two numbers, let's say a, b, that belongs to a real number system, which we called R, then we can definitely say that either a less than equal b, or b is less than equal a, or both. Suppose we have a set E. This is a set of real numbers. There may or may not be a number m that again belongs to R, such that every number in the set E is bigger, is less or equal to m. If there exists some m such that all a in A and a is less than equal m, then we said that a is bounded, upper bounded. If there is no upper bound, then the set is said to be unbounded above or have no upper bound. So similarly, we can define what we mean by lower bound by saying that if there exists some m such that x greater than equal m for all x in A, then m is a lower bound. So a set which has an upper bound and a lower bound is called bounded. Let's give one more definition. Suppose again E is a set of real numbers. So if there exists number m such that m belongs to E, and for all x in E, x less than equal m, then we called m as a maximum. So we say m is a maximum of set E. The same way we can define the minimum of set E. So for example, if we define the set of a closed interval 0 to 1 as all x is such that 0 is less than equal x and less than equal 1, definitely all points are that belong to this set are greater than equal 0 and less than equal 1, and 0 and 1 belong to this set 0 is minimum of the set of 0, 1, and 1 is a maximum of set 0, 1. The other interesting example is, let's say, so the other interesting example is the set of natural numbers. So the set of natural numbers has a lower bound, but there is no upper bound to it. To prove it, we need a couple of more definitions, so we will prove it in a little bit later. Now let's talk about the supremum and infimum. So as a motivation of describing supremum and infimum, suppose we have a set E which has some maximum M. Then to describe the M, we can say that M is the least of all the upper bounds of E. That is, M is the minimum of all the upper bounds. So M note that it is possible for a set to have no maximum and yet be bounded above. For example, if we take set 0, 1, which is an open interval, it has no maximum. So since 1 is a maximum, one open interval 0, 1 has no maximum but many upper bounds. So for example, 2 is the upper bound for this set, but so is 1. The least of all the upper bound is definitely number 1, and we can't describe it as a maximum since it does not belong to the open set 0, 1. Now let's define what we mean by least upper bound. Suppose E is a set of real numbers that is bounded above. That means there exists M such that x less than equal M for all x in E. If M is the least of all the upper bounds, it means M is the least of all upper bounds. So the other way to say it, if let's say C is also upper bound of E, then M should be less than equal C. Then we call that M is a supremum of E. The same way we can define the greatest lower bound, and we called it as a infimum. Couple of properties. So if E is unbounded above, then we say that supremum of E is infinity. If it's unbounded below, then infimum of set E is infinity. Any example of a non-empty set that you are able to visualize that has an upper bound will also have a least upper bound. The good question is, does this always true? Turns out that answer of this question is yes, and the property is known as the axiom of completeness. The axiom of completeness says a non-empty set of real numbers that is bounded above has a least upper bound. As least upper bound. At this stage, I'm not going to prove. Now let's prove a couple of advanced properties of real numbers. So the first property, which is very important one, we introduce it as a theorem, says the set of natural numbers has no upper bound. I will prove this one so you will have some intuition how to write this kind of proofs. So the proof is by contradiction. So we say, suppose by contradiction n does have a upper bound. So if it has upper bound, then we can use the axiom of completeness and say that from axiom of completeness it must have a least upper bound. Let's denote least upper bound as x. From here, by definition of least upper bound, we can say that n less than equal x for all and that belongs to our natural numbers. And we know that n less than equal x minus 1 cannot be true. So this is because x is a supremum of n. We can choose some integer m such that m is greater than x minus 1. From here, m plus 1 is greater than x. But this cannot be true since x is a supremum. So if it's supremum, it should be less than equal all natural numbers. So from here, we have contradiction. We prove that n does not have any upper bound. This theorem is known as the Archimedean property, and some consequences of Archimedean property are that if we given any positive number y, it doesn't matter how large is it, and we have other positive number x, no matter how small, we always can find some n which belongs to natural numbers and n times x is greater than y. So basically, if geometrically we say that there exists some small x and some y, we always can find some n such that n times x is greater than y. Now let's use Archimedean property and the axiom of completeness to do one more example. So what we want to prove that if x is some real number, then there exists an integer m such that m minus 1 less than equal x less than m. So geometrically what we want to prove, so if you give me some real number, I can always find integers and consecutive integers that x is between them. To prove this, let's first define some set S which has the elements all integers such that n is greater than x. So from Archimedean property, we know that this set is not empty. And it has lower bound. So from completeness axiom, we know that it has infimum. So from here, there exists some m which belong in S such that m greater than x, such that m minus 1 is not in S by definition of infimum. So from here, m minus 1 should be less than equal x and less than m. There is an there is an important relationship between the set of rational numbers Q and the larger set of real numbers R. So the rational numbers are dense. So what we mean by dense, it means the rational numbers are in every interval. Whatever interval we take, this interval, so if this is a real number, so this interval should contain rational numbers. So a set E of real numbers is said to be dense if for all intervals AB contains a point of E. The set of rational numbers is dense. So this is theorem, but the proof is not so difficult. It heavily relies on the Archimedean property, but we don't prove it. Now let's talk about the matrix structure of R. Usually we want to describe the distances between points. The distance of real numbers is either x minus y or y minus x, depending on which is positive. So for example, the distance between minus 3 and 4 is 7. To describe this in a general way, we need to define the absolute value function. Absolute value is function which is equal x if x is greater than equal 0 and equal minus x if x is less than 0. And it has some properties. So the property 1 is it's any x is between minus absolute value of x and absolute x. Second property is if you take xy in R, then absolute value x times y is equal absolute x times absolute y. This is what called the triangular inequality. And the last property is that let's prove a couple of them. So let's start by proving property 2, let's say. For example, let's prove property 4. We can define x as absolute value x as x minus y plus y. And from triangular inequality, this is less than equal x minus y plus y. So from here we have that the difference is less than equal x minus y. The same way we can write the same thing for y, and we will get that absolute value of y minus absolute value of x is less than equal x minus y. So from this two we can write that property 4 holds. Now, as long as we know the properties of absolute value and what is the function of what is the idea of the absolute value function, we can define the distance in R. So the distance between two real numbers x, y that belongs in R, then the distance is defined as absolute x minus y. The distance has the following properties: that x minus y less than equal 0 and x minus y is 0 if and only if x is equal y. So the second property is that x minus y equal y minus x, and plus z minus y. So the second property means that the distance is symmetric, and the third property is a triangular inequality. So let's do proof of third theorem, which is easy. So what we do, we deduct and add z. We can always do this, and we use the property of absolute value from the previous theorem and write it the following way, since we can the third property is proved. The same way we can prove that finite sum of absolute values is less than equal the sums separately. You can use induction to prove that. We can say that case 1, n is 1, then absolute value of x1 is less than x1. It's always true. For n equal k, let be true. So it's mean modulo absolute value of x1 xk less than equal x1 plus xk. Now we prove for n is equal k plus 1. So we want to show that xk plus xk plus 1 is less than equal this. From triangular inequality, we can write that less than equal xk plus xk plus 1. But from second step, we know that we can represent this as the individual sum of absolute values. And we prove that for any n, the sum of absolute sum of numbers is less than equal than the absolute of individual sums.